In this sketch, we present an image space technique which uses pixel shading hardware to generate outlines in real time. We will show the results of this approach integrated with hatched scenes, although outlining has broader applicability beyond non-photorealistic rendering. Image space approaches like ours have the advantage that the outlining task does not increase in complexity as the scene's geometric complexity increases. No knowledge of the scene geometry is required, making this an attractive solution, particularly in systems rendering with higher order surfaces. The three classes of outlines that we will detect and render in image space are object silhouettes and creases, shadow edges, and texture boundaries. These outlines are important visual cues which have previously been difficult to generate in real time. The general strategy presented here can easily be extended to generate other classes of outlines. Here we see a real-time physics simulation where many objects are interacting in a room with one light source. The point light source is also an active physics object, and we will occasionally show it in motion. The objects are being shaded using an extended version of the real-time hatching technique shown at SIGGRAPH 2001 by Brennan et al. Extensions to Brennan et al.'s techniques include per-pixel tinting of the tonal art maps to correspond with a base texture, and per-pixel tonal art map selection for more accurate lighting. The hatched scene minus the outlines is being rendered directly into the back buffer in two passes. One pass for unshadowed pixels, and one pass using the densest hatching pattern for shadowed pixels. For the cases of silhouette and crease outlining, we take a cue from Saito and Takahashi's 1990 SIGGRAPH paper, Comprehensible Rendering of 3D Shapes, and Philippe de Caudan's technical report on cartoon-looking rendering of 3D scenes. The goal of these approaches is to render a scene which can be easily edge-detected by 2D image filters. We render the full scene's world space normals and eye space depths into an RGBA texture using a programmable vertex shader to populate the four channels with these quantities. Here we see the eye space depth of the scene in grayscale, and here the world space normals in RGB. Once we have this 2D image, we process it to extract the edges. The processing is performed by rendering from this texture either into another texture or directly into the back buffer. The texture is sampled multiple times at different locations in the image by binding the texture multiple times with slightly offset texture coordinates. These multiple samples are operated on in a pixel shader, which amounts to an edge detection filter. The output of the filter is white for non-edges and black for edges. With this technique, creases and silhouettes both produce discontinuities in the image, and there is no real distinction between them. In this application, we have implemented the edge detection filters independently for normals and depths. These output edges can be composited with the already shaded scene using a multiplicative compositing operation to apply the outlines directly. Here we show the result of silhouette and crease outlining integrated with our real-time hatched scene. Now that we have outlined the creases and silhouettes in the scene, we would like to outline the shadows. To do this, we employ the popular stencil shadow volume algorithm, which alternately renders front and back-facing shadow volume polygons into the stencil buffer. The end result of this process is a mask of pixels that are in shadow for a single light source. Multiple light sources can be handled with multiple passes. Here we see the shadowed pixels for this scene. You'll notice that shadowed pixels on shadow receivers and back-facing polygons on shadow casters are both considered in shadow. Rather than filter the mask image visualized here, we use this mask when rendering the world space normal and eye space depth image to negate the normals and depths for pixels which are in shadow with respect to the light source in the scene. This creates additional discontinuities in the world space normal and eye space depth image which align with the shadow boundaries. This causes crease, silhouette, and shadow edges to all be caught by the image filter applied to the normal and depth image. The third class of outline that we wish to address is texture boundary outlining. Texture boundaries occur on the surface of a given textured object where an artist wishes to represent disparate materials adjacent to each other. Typically, these boundaries do not fall on a geometric discontinuity, hence the need for a separate technique for texture boundary outlining. Examples in this scene are the different patches on the soccer balls and basketballs, as well as the jewels inset into the chalices. To apply our image space technique to this problem, we use a variation on Orsad's priority buffers. The original application of priority buffers was shadow mapping, but we have found that its suitably authored priority, or ID map, allows us to outline texture boundaries. One issue that comes into play with the texture boundary outlining problem is sampling of the texture which defines the regions to be outlined. For example, if an object is rendered so that the ID texture undergoes extreme magnification, the bilinear filtering of the ID map can result in boundary edges which are not detected. Simply turning off bilinear filtering does cause the edges to be successfully detected, but leads to aliasing. To combat this, we have used large textures with linear map nearest filtering to reduce the number of pixels which require magnification texture filtering. Additionally, we have found that it is necessary to use multi-channel, that is, color IDs rather than scalars. This provides enough disparity between a region's neighbors so as to guarantee robust filtering. Now that we've detected all three classes of edges, we can composite them with the shaded scene. So far, we have shown edges detected directly from normal depth and ID images. To further customize the look of a given scene, it is possible to apply morphological operators to the outline images. Here we see our physics simulation with all three classes of outlines applied. Now we turn on one iteration of a dilation operator, which thickens the outlines in image space. This can be repeated by ping-pong rendering between multiple renderable textures before compositing the edge image with the hatched scene. We have illustrated a technique for using the pixel shading functionality available in consumer-level graphics hardware to solve outlining problems in image space. Our solution has involved rendering alternate representations of the scene into texture maps. The alternate representations rendered are carefully selected so as to contain discontinuities at the edges of features we wish to outline. The rendered texture maps are then filtered using pixel shaders to detect discontinuities. The outlines can be composited directly onto a shaded scene or further processed using morphological operators implemented as pixel shaders.